Okay, so no quiz this week. Instead, just work on extra unit 1 or unit 4, not unit 1, unit 4 practice problems. So use the time you would have spent to take the quiz and spend it instead on self-assessing where you are, making sure you're still staying up with the material. Homework is still due by tonight, but there will be no quiz this week. All right, questions on that? So discussion and homework due by tonight. All right, so use unit 4 practice problems to assess, like, do you understand the material? And if not, make sure you're learning it. So we're gonna move today into second order solutions. So far we've only looked at, so we're gonna look at specifically an example of a second order, which is an RLC circuit. And then we're gonna talk about the solutions, because with a second order solution, you can get different types of responses. So overdamped, underdamped, critically damped. Then we're not probably gonna get to this. So these two objectives are what we're gonna look at. So remembering the RC and RL transients. So when you had an RC and you move it from a source to no source, it's going to discharge. For an RLC, instead of just an exponential discharge, we're now going to see these 3 different types of responses. And so you're going to see, instead of an exponential, you're going to see the green one, which is considered overdamped. And you can see it kind of as a whatever you want to call that. So doesn't look as much like the exponential. The critically damped looks more like that exponential form. So that is the one where you're more used to a discharge type of look to it. Underdamped is actually has a complex root, and so you're going to see it oscillate like that due to the complex roots that it has. So 3 different types of responses based on the roots of the system. So remember back to roots, meaning a polar 0 from your Bode when we went through the Bode plots. So I had a lot of comments about the Bode plots, like, don't understand this as far as like application based, because it was more theoretical and you need to kind of know some of the terms to now we'll start talking a little bit more about the applications portion. So with that understanding, back to the Bode plots and the roots of the system, which are your poles or zeros from the equation itself. So when you get underdamped, this means that your roots are complex. For critically damped, that means that your roots, you have 2 of the same ones. So you have a and they're equal. So 2 roots that are equal. And for overdamped, this is when you have real roots. Meaning they're just there's 2 different fixed values for them. We're going to get into this in a minute with what those roots mean. So looking at these circuits, if we were to solve these, we remember that VL is equal to L di dt. And for capacitor IC, we know that C, the voltage across the capacitor dt. So with this knowledge, we can actually solve a circuit taking a loop. We have here that we know that Vn is equal to the summation. If we put ground here, it's going to be the summation of the voltages across the capacitor, the voltage across the inductor, and the voltage across the resistance. And that's going to be equal to Vn. So VC plus VL plus VR. We can then use the differential to express the voltage at the inductor will be L di dt, but we also know that IL and IC are equal, and so we can say that this is actually L, and the derivative of IC, which is C times dVc dt, which turns this one into a second order differential. So now plugging that in, we know that Vn is Vc, and VL is the LC d squared Vc dt squared, and VR is going to be your IC times I times R, and IC is the differential C, so this is RC dVc dt. So much fun, right? So second order differential equation. You guys remember how to solve these? So how would you go about solving them? So first off, what does this mean that we have, you go green. This is not a zero. So if you guys remember the homogeneous, I cannot talk today. Homogeneous solution was when you have it equal to zero. If it's not equal to zero for a second order differential equation, what does that mean? Thank you. It's a particular solution. So having a value here is just a particular solution. And if you remember, you can take the homogeneous, if I spell it right, solution plus the particular for your total solution. All right, so these are in series, and if you have them in parallel, you can do a similar solution. So here we would have this, and then we're gonna IR, IC, IL, and so we can do a current summation. So IS is equal to IR plus IC plus IL. And we know IC is C dVc dt. And here we know that the voltage across the capacitor is the same as the voltage across the inductor. So all this node is the same, and this one is the same. So these are in parallel to each other. So we know that the voltage at the capacitor is the same as the voltage at the inductor. And we know that VL, the voltage at the inductor, is L di dt, DIL dt. Okay, so IR, so I want to put these all in time in for currents. Let's see. So now I can substitute this back in for this one. So we get IC is C ddt, and then VL, which is equal to VC, is L DIL dt. So here IS and IR is going to be VL VL over R, and VL is L, so L over R, DIL dt. And IC is now this LC, d squared IL over dt squared. And then IL. So you can see the similarities here. You have a second order, and then in front of the second order, we have a value, and then in front of just the DIL dt, we have L over R. And again, we have LC here and RC. So this is tau, and this is tau. So that's kind of where, those are our time constants. They look just like the time constants from our RC and our RL circuits. So the differences are we have a VC and then we have IL. So just our variables are different here. So solving this differential equation, it's a second order linear homogeneous ODE with a constant coefficient. Is that equal to 0? So remember, you can write these and then you get a characteristic equation. From the characteristic equation, you get two roots. And then if your roots are real, then you can get exponential forms. So this is for a homogeneous solution. And for ours, we have that particular solution. So in Math 2250, which is why this ends up being a prerequisite for this course, is that you move to an easier way of solving these, which is using the Laplace transform. So the Laplace lets us be able to transform it into a different plane and then analyze the circuit a little bit easier. So with a particular solution especially, we can take the Laplace of this and we get that this transforms into RC, and then the derivative, remember, is SVC, and then if you have an initial condition, it would be minus VC of 0, so that initial condition. For a second order, you get S squared VC minus SVC of 0 minus VC of 0. So ignoring the initial conditions and writing this, we get just SVC plus LCS squared VC plus VC. And remember, our Bode plots are the output in this case would be VS or VC of S and then VN of S. And these are all in terms of S. So solving this for the VC of S over VN of S gives us 1 over LC squared, or LCS squared plus RCS plus 1. So this right here is our characteristic equation, and this looks familiar from our Bode plots, right? If we factor this, we then can look and find our exact roots. So factoring this to find the roots of this system are the poles of our system too. So if we were to graph this, it would be 2 poles. So characteristic equation and this is the homogeneous solution here. So we have ignored the initial conditions. All right, so it's going to be way easier to solve it in this frequency domain. And so we want to look at, can we transform the elements themselves and then analyze this by using resistors. So we're moving to, this is called impedance, which is Z because it can be complex. And so moving our elements into the Laplace transform domain. For a capacitor, we know that VC is equal to IC. IC is equal to C dV C dt. And so this becomes your Laplace transform of IC, and then CS, and then VC. So remember, resistance is the voltage is equal to I times R. What do we notice here R would be then? So if we divide this over, I'm going to say that the Z of the capacitor, so instead of R, it's Z, meaning impedance, will be equal to what? Correct, just 1 over CS. Then for an inductor, we know that VL is equal to L dIL dt. And if we transform that, this becomes the transform of VL is equal to LS and the transform of IL. So what is the ZL going to be? Sorry. What's ZL going to be? Thank you. LS, correct. So what this means is that these can act just like resistors, and then we can treat them just like a resistance. So if they're in series, we just add them. If they're in parallel, we take the parallel form of them. And the only difference is that they have these S's in them. So with an S, though, we can get this characteristic equation, or not characteristic equation, we can get the, oh goodness, output over input. We can get your output over input equation just by using our current techniques without having to go through the whole transform and then create that from the differential equation. And so this is going to be a way easier technique to be able to solve these problems. So directly we could go back and transform these. So your R stays the same as R. This becomes SL. This becomes 1 over CS. And let's see, this was solved for VC. And if we were trying to find VC here, it would be a voltage divider. Or we could find the current and then take I times R. So same techniques we've used before if these were all resistors. So VC here is going to be VN times 1 over CS all over 1 over CS SL plus R. You can multiply the top and the bottom by CS, and then this becomes VN over 1 plus LCS squared plus RCS. Same exact equation. And it was really quick to get. Yes?
Are we told to find the voltage across the capacitor, or are we just finding that because the voltage across the capacitor kind of is hooked into all the other voltages?
I was doing that because the example I gave was solving for VC.
Oh.
So that was the only reason. I wanted to compare that, yes, these are the same. So this ends up being this exact same equation here, but much shorter, because I can look at it and directly say, like, I can use my circuit techniques and now write this equation kind of almost immediately. So way easier to do than writing out the time domain, differential portion, and getting that second order. The other powerful thing about this technique is that you can do it for any order. This is a second order that we're looking at the example for, but you can do this for 5 elements in there, which is going to be a 5th order differential equation that no way do I want to solve that one in the time domain. So it makes it very nice to be able to solve these in a quicker way. So very powerful technique to use this Laplace. So from this is exactly the same. And we could do the same thing if we were trying to find any voltage or current within this circuit too. It doesn't just limit it to the voltage across the capacitor. We could find this for the voltage across the resistor, the voltage across the inductor, the current through there, and it's really an easy way of writing it really quickly. So the current here, I of S, is going to be Vn over R plus SL plus 1 over CS. Then we can manipulate that algebraically and get a polynomial, or we can factor that and get 2 roots of poles in the denominator. So going back to this one, okay. So for this one particular example, if we want to now go, oh, and I didn't write this. So R just stays the same as R. It has no change because it doesn't have any time dependence on it. So it's R in time domain and R in the frequency domain. So you can do either transform, Fourier or Laplace, for the elements. So this is showing you to go from Fourier and Laplace, the only thing you have to do different is substitute j omega for S. Sorry. To Laplace. So changing between the two, j omega equals S. So that's the only difference. So instead of 1 over SC, you substitute in S as j omega. And here is going to be the same. So this one is the Fourier representation of it, and this one is the Laplace representation of it. Okay. So we're just going to take a second and think about interpreting these impedances. And so for a capacitor, if you have a very low frequency, what happens to it? It does what? So if C is like 0, what happens to that one? 1 over 0, what happens? It's really big, right? The limit of that as it goes to 0 ends up being like infinity. So what does that look like? Really big, which is an open or a short? Open, correct. So that one looks like an open. At high frequencies, it looks like what?
I'm just saying it's like acts similar to like resistance, like a super high resistor would create like a
Correct. Yep. So if it's 1 over a really high, say 1 over infinity, what does that go to? A wire, because it will go to 0. For the inductor, what happens? A very low frequency, it looks almost like a wire, and then at high frequencies. Okay, so for DC, what is your frequency for DC? Do you have any frequency? No. So what does it mean? You have 0 for omega, so what is this? Capacitor looks like a 1 over 0. Open. Inductor, if it's 0, it again looks like a wire. So this is why we model that capacitor as an open after sat there a long time and you have DC values on it. So anyway, that's where the model comes from. Okay, so now all of what we've been able to do before work. So you can use Ohm's law, series parallel combinations, voltage and current dividers. I don't know what that was. All right. And then we can use this to find the transfer function, which is your output over your input. For any circuit that has more than just one time-dependent element in it. As I said, you can have up to 10. I mean, you can have 10, you have 20. You can have a lot and very big, complicated circuits. So this technique is very powerful. What we're going to go back to now is just talking about that RLC circuit and then looking at that transfer function and then converting it back into the time domain solution of it. So what we're going to need to look at first is that characteristic equation. It was a polynomial, so you know it factors into 2 solutions. So you have different options of those solutions. So to remind you, you can take the quadratic equation of the 2 roots, and then, that's minus b plus or minus the square root of b squared minus 4ac over 2a. And then you get these 3 options. You may have that this value is greater than 0, which means that your roots are real. You can have double roots when they're equal to 0. And then you can have imaginary roots, which are complex roots when it's less than 0. So that is the case that we're going to get here, is that you're going to get those 3 different transient behaviors in the time domain from depending on your root values. So again, the underdamped are those imaginary roots, which are going to give you an oscillation because they're complex, which makes sense that you're going to have some oscillations. Critically damped is going to be when you have a double root, and then overdamped is when you have just real roots, root values. So the time domain solution part is going to be dependent on the particular solution and then the homogeneous solution. So for overdamped, which is two real roots, here, it ends up looking like two exponentials. And then you're going to get the particular solution that is going to be just the value. If it's the voltage across the capacitor, it's going to be the value at that final time. And that's all you have to do to find that particular solution, which makes it really nice that we draw the circuit in the final time, solve it for just that voltage across the capacitor, and then we know the values. We'll talk for a minute about these values in a second, and then these are your root values is going to be the exponential portions of it. So this is going to be a final value. So let's look at this particular example. So with this, we get, we already did this solution. So it's S squared plus R over L S plus 1 over LC equals 0. In this case, R over L is going to be 90 over 20 milli for 4,500. And 1 over LC is going to be 1 over 20 milli times 10 micro for 5 times 10 to the 6th. And then our roots is going to be the solution of that. So A minus B, which is going to be 4,500, plus or minus the square root of 4,500 squared, minus 4, and then A is 1, and 5 times 10 to the 6th. And then A is 1 again, so 2 times 1. So this ends up being a minus 2,500 and minus 2,000. So these numbers from a circuit are going to be default units of radians per second. And remember that the default unit was volts per volt of magnitude. So this goes back to those Bode plots where when you find the transfer function, your voltage there will be volts over volts, and then these values of roots are going to be radians over per second. Radians per second, yes.
That initial equation to the denominator that we have above, right?
Yeah, so from, go back, I can copy it from here. So either method that you wanted to use, this was the method where I just wrote it directly, or you could go through the time domain. So this was our equation, and then to get a 1, I just divided by L over C. So I brought LC out, and this became S squared plus RC over LC, S plus 1 over LC. And then that LC is just a constant number. So remember from the Bode plot when we did that, that just shifts it value-wise. It doesn't do anything with the roots of the system. So here we have two real roots of the system. And so the form of this solution is going to be the I of t is I infinity plus e to the minus 2000t, 2000, plus the d value e to the minus 2500t. So these are going to be found. So each of these values of the variables here is found by the initial and final conditions. Okay, so for an initial condition, so for your initial condition, remember this is at time equals 0 plus. So right before the switch, so remember that the capacitance, or the voltage across the capacitance, VC and IL, have to stay the same. So what are those values? What is IL before the switch? Yep. And what's the voltage VC before? It's going to be 0 too. So when they switch, a very good one. There we go. The IL is going to look like an open, and the capacitor is going to look like an open. So you pretty much, sorry, didn't draw the resistor in there. There we go. Okay. So that makes it easy. These are going to stay both 0 at 0 plus 2. So 0 for our initial value. And since we're looking at the current there, our initial is going to be 0. At infinity, your switch is closed. And again, your capacitor is going to be open and your inductor now is a wire. And again, your current's going to be 0. So let me copy this. So looking at this, we can look at that initial time of 0. So here, if we put in 0, this became 0. And what happens to e raised to the 0? Correct, it goes to 1. So if we put a 0 here, 0 here, these become 1. So we have a 0 equals b plus d. So we have b is going to be equal to minus d. And then we can take the derivative to find the next one. So going back to that, I'll take a second. We know VL is equal to DIL dt. And so, L. So VL over L equals DIL dt. And so VL in this case is 12 from the voltage, and L is given as 20 milli. So we can use this to find the other initial condition, and so this ends up being 600 12 divided, 2 comes up 6, and then 3, 600. So we use that 600, and then we would take the derivative, so this becomes a minus 2000 b e to the minus 2000 t, and then a minus 2500 dE to the minus 2500 t. And again, at 0, these become 1. And we know that B is equal to the minus D. And so we can plug one of those in. And we can solve for one of them. So solving for B gives me 1.2. And then D will be a minus 1.2. So this sounds really interesting because we have an initial value of 0 and a final value of 0. So most students at this point go, well, how do we have anything else? So what this actually looks like is that it will go up. I want this one. So you're starting at 0, and then your final ends up being at 0. So it actually kind of goes up, and then it goes down. So it actually looks more like this in your current. So your final current of your time domain expression ends up being a plus 1.2 e to the minus 2000 t minus 1.2 e to the minus 2500 t. And this would be your time domain expression. Questions?
What happened to the I of infinity in the equation? Is that become 0?
Yeah.
Oh, yeah, we just solved for that.
Yep, we solved for it, so it's always 0. Right, so this is actually a better graph than I can draw there. So there's your actual graph. So it does kind of go up, and then it goes off. So your book has a very nice table that already has these values calculated if you can identify if your circuit is a series or parallel form. So let me go down to the table. So the nice thing here is that it already has calculated these constants for you, and all you have to do is look for the final value, the initial values, and the final values. And then knowing your roots, you can just put these into these equations. So you don't have to do that every time. So it can make it a little bit quicker to solve. So that was the overdamped example that we went through, and we did it for a series RLC. And then a parallel RLC is very similar. Again, you can just find the the initial and the final values for the currents and the voltages, and then you can use the equations to find the constant values. So those are when you have two real roots. We're going to look at the case where you have critically damped when they're equal roots, and then when you have the complex roots. And we're going to, so to determine which ones you have, you can actually look at this alpha. And alpha is part of that characteristic equation of the roots. And so you can find for the series or parallel just by looking at the circuit instead. What is this circuit? Is it critically damped, overdamped, or underdamped? And then you're comparing that alpha with your resonant frequency. Remember that resonant frequency for an LC circuit we found, whether it was in series or parallel, was 1 over the square root of LC. And so we can calculate those values and then calculate the rest by these equations instead of having to rederive them every time. Does that sound easier? Okay, so let's go through an example.
In the table, why is the series, it's only calculating voltage there, in the parallels calculating current?
So with the parallel circuit, when we solved them, you saw in the beginning, it was because we had the differential for the I of L equation. And then in the one that was in the series one, we did it for the voltage. You can do it for the other variables in there too, but the equations are only valid for those particular ones for these constants. But as I showed in that method, you can do it for any variable within the circuit, but then you have to figure out the constants of it. And you have to go through that method to find those constants. The other way is to find it this way and then use that equation in your to solve for the other ones. So if I know, for example, that the current for a series is the same as the current going through the capacitor, so I can use the voltage there to then find the other current. Does that make sense? Okay. So this table is only valid for that current or voltage, but you can actually solve it without that. Okay, so the next one we're going to go through, we'll use the table this time. I think it's critically damped, yeah. Okay, so for critically damped, one we have to identify, is this circuit a series or a parallel to be able to use the table? So how do you know if it's in series and parallel? You're going to look at the connections between the inductor and the capacitor. So hopefully here it looks very obvious, like these are in series. I don't think I have an example yet of parallel. Next time we'll go through more examples of identifying is this in series or parallel. Okay, so critically damped series. I'm going to grab the equations from it. Okay, so first off, we need to figure out which one is it? And so we need to figure out the alpha value and the omega naught value. Okay, so for this particular one, alpha is going to be, we're in series. Back up. And then omega naught is always 1 over the square root of LC. So this one we identified was series, so alpha is going to be R. That was weird. There we go. Okay, copy. R, and that R is what we have to figure out. So your R is going to be the equivalent resistance in the circuit. So This one's pretty easy. Hopefully R is just R here. Does it not have a value of R? This should be 10 ohms. Okay. Critically damped. Just make sure. Yeah. Okay, so 10 over 2 times 20 milli gives me an alpha 250, and omega naught is 1 over the square root of LC. So 1 over the square root of 20 milli times 10 milli, or 10 micro. One, 2, 3, 4, 5, 6, yeah. So 2,236. So you compare alpha and omega naught, and omega naught is greater than alpha. So going back, or these should be equal. They're not equal. There must be a different value of R that was used, sorry. Underdamped, critically damped. Okay, different value of R was used, sorry. Okay, you can also design your circuit by solving these and then picking a value for R to get you in whatever mode you want to be in. So this is 89.4 ohms. So 2,235. Okay, so these are approximately the same, so we're going to just assume that they are the same. So alpha equals omega naught. So critically damped. So for this critically damped, we need to know the B1 and the B2, and then our voltage at infinity, and B1 and B2 is found from the current and voltages at the initial time and at infinity. So we're going to redraw the circuits for each case. So at t equals 0 minus, we already did this, so that makes it easier. So we have IL is 0 and VC was 0. And at infinity, we'd also found that, so IL again was 0 and VC is 0. So wait, I must have did something wrong. Characteristic equation, B. IC of 0. Okay, so this is IL of 0. No. Okay, I'm doing a brain. So there is a variable in there. I'm just trying to see why am I missing it. Because your B2 is not 0. VC at 0, it's going to be 0. VC at infinity. Oh, VC at infinity is not 0. That's where it is. Okay. Okay, at infinity, your inductor goes to a wire and your capacitor goes to an open. So what's your voltage across this? It's going to be 12 volts. So your capacitance voltage at infinity will be 12. And your current will be 0. So B1 so this goes to 0 and this goes to minus 12 because it's a minus there, and then B2 IC of 0 will also be 0 because this is equal. So this will be 0, this will be 0, and this will be 12. So then it becomes A plus alpha, which is 2235, times a minus 12, which is 600. I get a minus. So B1, that's not. Okay, you're gonna get the same at infinity and it. Okay, I'm gonna think about this more. There's something going on with that one. The solution should look like this, critically damped. It will go up and then it will be 600 TE to the minus 2,236 T. I'll figure out why I'm missing those constants in there. Just as something weird. Okay, questions though about the process? Yes.
How does it differ for IT? Because I mean, the original equation we solved for underdamped, we did IT.
Uh-huh.
We only have the formula for VT. How does it change? Like, is there a separate table for?
So say that again
Is there
for.
a separate table for solving for the current? Because that table's only for voltage.
Correct. So the. Oh, that's probably where I'm going wrong. So the voltage, yeah, that's why. Okay, that's why I'm. Thank you. That is more clear. Okay, so the table is for the voltage. Then to get to the current, that's why these numbers are weird. Okay. So you can find the constant. So here we did it with the current instead of using the method of the table. So with this one, you can find the constants by finding the initial values and then setting the equation and then taking the derivative of it to find the other one. And in this case, once we find VC of t, we know that the current is going to be the derivative times the capacitance of that. So we would find the equation first for VC of t, and then IC is going to be the C dVC, the derivative of that times C. And that's how we will get that equation. So I'm gonna rework this and we'll go through the solution next time. All right, so for the underdamped case, again, you're going to find alpha and omega naught and compare the two to discover if it's underdamped, overdamped, or critically damped. And then from there, you're going to use the table to find if it's underdamped. Now we have complex roots, and so we're going to end up in the time domain with a cosine and a sine. So then we want to find that frequency called the natural frequency and the damping coefficient. So for underdamped, we're going to need to know a couple more values. So that damping coefficient ends up giving us a wide range of how the actual oscillation is going to look. So for 0.4, which is the lower values, so this is 0.4 versus this is like 3.0 is this line there. See if I can go over it. So in contrast, a 3.0 damping coefficient versus a 0.4, which goes up, down, and has a very significant oscillation in there. So that's the damping coefficient determines how much is that going to oscillate. So you can see from that graph the differences in those oscillations. So we don't have time to go through the full solutions, so we will go through these two cases. Next time we'll go back over that. The one I struggled with today, a critically damped case, and I'm going to rework it just to make sure where I'm going wrong. And then the underdamped case. All right, see you guys next time. Yeah.
Is there any way we could push the homework due date back to June 20th?